Hey folks, so my name is Leybzon. I'm an MLOps architect at YLabs, and what that means is that I go around to conferences, to meetups, to user groups, and I try to talk about YLogs as well as YLabs. And I'm going to dive into what both of those things are. But before I do, let me give you kind of an overview of the presentation that I'm going to be delivering. So as you can see, the very clunky title of today's presentation is Save Your ML Model from Degradation with Data Logging. And fundamentally, what this means, what this is getting at, is that machine learning models degrade over time, right? They perform worse and worse. And the reason for that is that data changes over time, right? The real world generating data changes over time. And in order to be able to prevent that model degradation, we need to be able to log the data coming into the system and log the predictions being made by the system so that we can be alerted when the performance is degrading. So that's kind of a high-level overview of the talk. Now let's dive into the agenda and go through what it is that we're going to be walking through today. So there's a few different components to this talk. First, I'm going to be talking about the ML workflow and kind of just setting a baseline expectation so that we're all on the same page, we're all speaking the same language as to what it is that it takes to deploy a machine learning model in production. From there, I'm going to talk about data monitoring and observability and make a point about how data monitoring and model monitoring are actually the same thing. From there, I'm going to go on to talk about the fact that monitoring requires logging, which segues nicely into my introduction into YLogs, which is the open source standard for data logging. And then finally, I'll be able to answer any questions that y'all might pose in the chat. So I want to start off today's presentation by pointing out that I have a tendency to talk a little bit quickly. Especially when I get excited about a topic, I just ramble on and on. Please, if you don't understand something that I'm saying, if there's some term that seems ambiguous or some concept that might be missing in your knowledge graph, please feel free to ask a question during chat or in the chat. I'll try to get to it in the presentation because in all likelihood there are other people who are thinking the same thing, but there's a possibility that I'll hold off until the end of the session to answer your question. But please don't hesitate to ask any kinds of questions that you might have in the chat. So let's start off by talking about the ML workflow and talking about the different constituent components, the different steps that people have to go through in order to take a machine learning model out of the sandbox, out of the development environment, and be able to actually deploy it so that it's running within the context of a broader application so that it's actually generating revenue for the business, right? So at the very start, we've got model building, right? We've got training the model, playing around with different versions of a model. We've got some training code, some training data that this code is run against. And at the end of the day, we're going to be producing a few different models. From there, we're going to be evaluating these different models against each other, maybe experimenting, doing some hyperparameter tuning. And from there, we're going to be selecting a single model that is going to get first productionized, so turned from a model object in whatever language is being used to building the model into the model language, into the language that the model is actually going to be deployed in. So very often your model gets trained in Python, but gets productionized into Java or C++, whatever the environment that the production code is running in. From there, the model needs to be tested. You need to make sure that it integrates with the rest of the application. And finally, it can get deployed, right? And at that point, you've got a model running in production, right? Which means that it's generating revenue for your business. It's doing whatever it is you've trained this model to do. Classification, regression, doesn't matter. You've got a model in production. Now, a lot of folks, unfortunately, stop here. They say, okay, I've deployed my model. Let's go on to the next one. Well, that's not really how software applications work. Right? Anybody who's familiar with classic DevOps practices, with software engineering standards, knows that it actually takes a lot of monitoring and observability to be able to maintain the quality of a piece of code. And models are no exception. In actuality, models have the potential of degrading even faster than other types of code, and therefore require a lot more monitoring and observability. And I'll talk about the distinctions between DevOps and MLOps a little bit later, but hopefully this gives us some perspective on how model monitoring and observability fit into the ML workflow. And now let's talk about the importance of monitoring and observability, because, you know, it's one thing for Danny to be telling us, okay, yeah, we need to monitor our models, fine, but like, whatever, I've got other stuff to do. And it's another thing to realize what happens when you deploy your model to production and you're not keeping an eye on it. Because the fact is, as the slide points out, if you're not keeping an eye on your model, your customers are. Now, you know, this is like, I'm sorry, it seems like there we go. Can you all see this slide okay? Oh, I guess I'm the only one that can talk. It looks like we can see the slide okay. So as the tweet on the right-hand side points out, there can be times that a model really messes up, right? That it gives a crazy prediction. It makes just a really faulty choice. As we can see in this situation, a machine learning model is recommending a whole pepper, a bell pepper, when somebody actually wants some roses for their wife. Right? And this is kind of a ludicrous situation, but it's something that really happened on Amazon's website. And the fact is that this type of model performance degradation can absolutely be prevented by somebody monitoring their model, right? By tracking to see what the predictions of the model are and making sure that those predictions make sense in the real world. And again, I'll talk about a little bit more about how to actually do that, how to implement it. But first, I want to just establish that we're all on the same page, that this is an important thing to do. One other quote that I'd love to share with y'all that makes a really compelling point about this, and I wish the slide on the screen updated at the same time that mine did. So there's a quote by the chief decision scientist at Google, Cassie, which says, how to avoid AI pitfalls. Repeat after me. The world represented by your training data is the only world you can expect to succeed in. One more, the world represented by your training data is the only world you can expect to succeed in. What this pithy quote is saying is, as the real world changes, if you're not constantly updating your model, which, like, let's be real, nobody is really doing online learning these days, and constantly retraining your model in order to be able to take into account changes in real world processes is pretty computationally expensive. But if we're not doing that, which again, most of us aren't, then the result is that over time, our model isn't going to be effectively modeling the real world, right? There are lots of different types of changes that occur in the real world. Maybe something as big as COVID, right? Which dramatically change people's shopping habits, their viewing habits online, the way they interact with other people, the way they interact with the world, right? But that's a very extreme example, right? Of all of a sudden, there's a massive world event. But even slower, more progressive changes take time, but this evolution results in model performance degradation over time, caused by data drift, by covariate drift, by semantic drift, whatever the underlying cause may be. The result is that your model decreases in performance over time, simply as a result of the fact that the real world is a dynamic and ever-changing place. So, okay, hopefully at this point we've established the need for machine learning monitoring. Let's move on to talk about how to do so. And one hypothesis that I'm going to put out to you is that there's actually no such thing as model monitoring. It's impossible to really monitor the internals of your model because, as we've all probably heard a million times at this point, machine learning models are a black box. And now plenty of people are doing really cool, interesting work to try to open up the black box, to try to produce metrics about why is this model doing this thing. They're working in fairness and explainability, interpretability. They're doing really cool work in this field. But I mean, to be totally frank, it's just not that developed yet. SHAP, all of these state-of-the-art explainability and interpretability algorithms still don't really give us a deep understanding of why is this model making the choice, and understanding why isn't the only thing that we need to monitor, which is why I propose to you that really we don't want to do model monitoring, we actually want to do data monitoring. And the reason for that, the reason that we want to monitor the data going into our model and the predictions coming out of our model, which are themselves just another type of data, is because ultimately we want our model monitoring to be able to answer the most common questions that we have, right? The top question that somebody might have is, how is the model performing? Right? And maybe you've got like a ground truth metric that you can use to evaluate how my model's performing. Maybe I'm making a prediction and then finding out in real time whether my prediction was correct or not. But there's other questions that we might have as well, right? Should I be worried about data drift? What did my training data look like? What was the input data to the model yesterday? How was yesterday's data different from today's? How was yesterday's data different from last week's data? Well, you might notice kind of a common trend in all of these questions, right? Although they're all questions about models, most fundamentally they're questions about data. So we need to be able to answer questions about data in order to understand the predictions that our model is making and in order to be able to monitor our model. So to monitor our model really means to monitor the data coming in and to monitor the predictions being made by it. Okay, so hopefully now we've established that data monitoring and model monitoring are kind of actually synonymous and that we need to do the latter in order to be able to do the former. Okay, talked about why it's important. We've talked about the fact that model monitoring is actually data monitoring. Now let's talk about how we can do monitoring. And the answer is that any informed DevOps engineer is going to tell you that monitoring any kind of application requires logging, right? The first step to monitoring any kind of application is logging. How can I know the internals of my system if I'm not getting a record of the system itself? And this insight from DevOps is something that we're going to cross-apply into MLOps. And I'm going to dive into those two terms a little bit deeper now. So in DevOps, in development operations, we might ask questions like, is my application performing well? If not, what about it isn't performing well? And what can I do to ensure that it does perform well in the future, right? DevOps personnel are tasked with reliability. They're tasked with making sure that applications being deployed into production are able to perform and able to continue to drive value to the business. All right, now let's look on the other side, right? We've got MLOps. So in the MLAI world, we might ask questions like, is my model performing well? If not, what's causing it to not perform well? And what can I do to ensure that it can perform well? You might notice there's kind of a one-to-one relationship between the questions that a DevOps engineer might ask and the questions that an MLOps engineer might ask, right? Because ultimately they're tasked with the same job. They take an application, be it a classic software application or an AI application, and they want to make sure that it's deployed in a robust way that's easy to maintain and continues to provide value for their business. Okay, so we can see a lot of parallels between these two worlds. Now, let's talk about what logging looks like in DevOps versus what it might look like in MLOps. So in DevOps, we're monitoring applications that are running on top of systems. So we might take some system logs like the host name, a process type, a log type, an application, an action, TCP socket status. We might be monitoring certain things about the underlying hardware that's actually running the application. So like CPU, memory, storage, IO. We might be monitoring stuff like the response time and the load. All of these things are helpful to monitor and very important to log so that we can monitor them. Now, in the MLOps world, conversations about logging are actually still very immature. We've had really good logging tools in the DevOps world for a while. We've got StatsD, now we've got OpenTelemetry. There are all of these different tools that help people log classic applications. But in the MLAI world, we're really still developing the tools that we need in order to be able to log our data, which is what we need to be able to monitor our application, our machine learning models, as we talked about previously. So, okay, one approach that's taken to logging is data logging, which relies on sampling. Which requires taking an entire feature vector and basically subsampling the population of data that's being fed into the model and subsampling the predictions that are being emitted by it because it's ungainly to deal with the entire data set. Okay, sampling works pretty well in a lot of circumstances. I'm going to be showing you why sampling doesn't work super well when it comes to monitoring by talking about long tails on distributions and the need to capture more granular data about the edge cases. But okay, like sampling works okay in the real world, and maybe it works okay in monitoring. But there's a much more elegant and a much more interesting way to do this, which is profiling. Right? Instead of taking a sample of each data point, you extract statistical properties of each feature. So instead of representing the entire feature vector, instead you pull out certain key statistics that can be used to describe the distribution of the data. And in doing so, you actually get to monitor a lot more components of that, right? You can start tracking missing values, you can track cardinality, the type of data, you get your summary statistics which make up the profile, you can pull out a top K, and you can even deal with unstructured data, right? So there are these two different approaches, sampling and profiling. And I'm going to talk about why we probably would prefer to do profiling, why I think everybody should be doing profiling. But before we dive into that, let me describe to you kind of what the optimal logging tool might look like. So if we ask the question, how do you test, how do you monitor, how do you debug, how do you document your data? The answer is that we need a data logging tool that has a couple of properties. We want it to be descriptive. We want it to be lightweight, and we want it to be mergeable. So let's talk about each of these terms one by one. So for a log to be descriptive, it needs to be telling us what's going on, right? And in the case of data, we really want to have kind of a summary, a snapshot view of like, okay, what does my data look like at this time? So we probably want to understand the distribution. We want to talk about missing values, all of these different components that I had touched on earlier. Now, in addition to being descriptive, we also want it to be lightweight, right? I think this makes intuitive sense for a lot of us to the point that maybe it doesn't even need to be said, but just so that we're all on the same page, you could get a fully descriptive set of your data by just having the entire data, right? But the issue with that is that it's not lightweight. Moving around your, megabytes, gigabytes these days, like terabytes, zettabytes, who knows, of data is totally unreasonable to do for the purposes of monitoring. Monitoring needs to be able to take in lightweight logs and produce insights for human beings out of them. So it's really important that our data logs be similarly lightweight. Now, in addition to being descriptive and lightweight, a thesis that I have is that logs also need to be mergeable, right? And I'm going to talk about the key characteristics that mergeability enables, but from a high level, mergeability is really powerful because it allows you to take advantage of both, to monitor and log on both distributed systems as well as on streaming systems. And again, I'll talk about this a little bit more in a few slides. So, okay, we've kind of discussed what it is that we want out of our logging tool. And as you might imagine, I kind of have a point of view about this because I've been working on a logging tool for a few months now. And other people at the organization that I work for have been working on it for several years. So if you want to check out this open source project that we've been working on, you can navigate to bit.ly/YLogs, which is, as described here, logging for the ML stack. So it's a library that implements profiling, this statistical technique that I described earlier, in order to be able to generate logs out of data. And those data logs can be used for a number of different things. It can be used for data ops. It can be used to do data quality assurance, to do a lot of things. But it's built by machine learning engineers for machine learning engineers. And really the original intention was using it for ML monitoring. So this is a little description of the YLogs project. So before YLogs, data is ephemeral, right? It's constantly changing, it's moving, it's flowing, it's going into the data lakes and the data rivers, the data clouds. I don't even know all the buzzwords that people use these days. So before YLogs, we've got this overwhelming, complicated streaming process that can be really hard to keep track of. Now, with YLogs, we can actually use a standard format for representing a snapshot of the data, right? We can take these profiles, which effectively are photos. They're effectively brief summaries of the data at any given point in time. And we can use this standard format to be able to say, my data has changed over time, which indicates to me that the performance of my model has been changing too. So YLogs creates a standard format for representing a snapshot of data. Now, one thing that I really want to highlight about YLogs is how easy it is to use to profile data. It literally takes just a single line of code in order to be able to log a pandas data frame, log an image. In the future, we're going to be adding support for video, for audio. We've got a string tracker, which enables you to log unstructured text data as well. So you can log all of these different types of data all in one place with this single line of code. Okay, so I had mentioned earlier that I was going to dive a little bit deeper into the distinction between sampling and profiling, and this kind of reinforce for you this hypothesis that I have that profiling is a better approach than sampling. So YLogs profiles use 100% of the data. They don't take a sample of it. And from that 100% of the data, we create kind of a compressed version that allows you to capture the distribution. So like basically a histogram view of what the data looks like. Now, capturing distributions from sample data is obviously less accurate, sometimes significantly, depending on the level of sampling. And what we can do here, what we've done here is actually ran a benchmark test where we hold side by side what happens if you do sampling and what happens if you do profiling. Now, the y-axis here is the median error, or the error on the median, rather. And as we can see, the error on the median is quite a bit higher for sampling data sets than it is for profiling data sets. So in some cases, there's a near zero error if we choose to profile data versus a very, very high error if we sample. In other situations, the profile might not be able to adequately capture all of the information in the data set, in which case it might introduce some error, but still significantly less error than if we're using sampling. And this is the case for a number of different distributions. And the reason for this most fundamentally is that sampling is really, really bad at picking up edge cases, right? If we think about data in the real world, right, there's kind of two broad families of distributions that we can think about. We can think about symmetrical, more like Gaussian or normal distributions that have a kind of a fat center and then kind of trail off in either direction. But in the real world, a lot of data is actually comes from more of a power law or a Pareto distribution or a Poisson distribution, which are all distributions with a long, long skinny tail at the end, which means that there is, although a low probability, a non-zero probability of some tail event happening. And as we know, these tail events often get missed by sampling, right? If we choose to sample data instead of profiling it, there's a good chance that our sample isn't going to be picking up on this really tail end event. And that's unfortunate when you're trying to monitor a system, because realistically that tail end event, this like extreme outlier, is exactly the thing that you should be worried about, right? It's these outliers that are the main driver of model performance degradation and are really the main thing to be picking up on. So for all of these reasons, I think it's pretty fair to say that you want descriptive logs, and that the best way to get descriptive logs is actually by profiling rather than sampling data. Another component that we want is we want our data logging tool to be really lightweight, right? And here we've done another benchmark analysis where we took a few different data sets, classic open source lending club, NYC tickets, and pain pals in the US. As you can see, they ranged in sizes from a couple of gigabytes to dozens of gigabytes. They've got anywhere from 2 million to almost 200 million entries. And after getting compressed, they're all approximately 14 megabytes. So after going through the process of being profiled with YLogs, they are quite a bit smaller than they were previously. And the reason for this is because we're able to effectively capture the distributions of the data, effectively capture descriptive statistics that tell us all that we need to know about what the data set looks like without having to have the data set itself, right? Because the data set has all of this extra noise, this non-useful information. We're able to extract the useful information out of it and only monitor on that. So from here, let's talk about why mergeability is an important feature. So mergeability is important because it enables distributed and streaming systems. And what I mean by this is that a lot of the times in the machine learning world, we're not deploying a model just once in one place, right? Think about like if we're Netflix and we're serving the Netflix recommendation algorithm, there is not a lone computer running the Netflix recommendation algorithm. It's distributed across an entire cluster, which auto scales in response to load. Right? Now, these distributed systems inherently are going to be producing more logs, right? You're going to be producing logs for every node in the network. In the case of like deploying a machine learning model, every place that the model is deployed, you're going to need to generate some logs there. So the ability to merge together the profiles from these different sources enables us to analyze the system as a whole instead of getting caught up instead of analyzing each log individually. Basically, mergeability enables us to not mistake the forest for the trees and really analyze the forest as a whole. And the other thing that mergeability enables is streaming systems, right? If we've got a streaming system that's bringing data progressively in micro batches instead of in one large batch at a time, the ability to generate the profile and then to merge it into the previous profile means that we're able to maintain lightweightness on a streaming system without having to compromise the descriptiveness of the profile. So mergeability is also a really key attribute. So one really powerful thing about YLogs is its ability to integrate with a number of different tools, right? Whether you're using Spark and you're going distributed, whether you're running on a single node in Python, you got your data in pandas, if it's unstructured image data or text data being represented as like raw text data in Python, doesn't matter. It doesn't matter if you're using MLflow, if you're using another deployment system. We've got lots of different options here, and we integrate with all of them. And the reason for this is because we have a very strong hypothesis about what logging should look like and how you should monitor your model, but we leave it up to you to decide how to deploy your model, how to productionize it. So in response to the question, how do you test, monitor, debug, and document data? The answer is that you can test, monitor, debug, and document data with YLogs, this open source library that I highly recommend anybody who's doing anything related to data ops, to MLOps, machine learning monitoring, deploying machine learning models in production. Highly recommend that you go check out this, this project. And importantly, maybe most importantly, I actually have an incentive for people who want to go do this. So if you go to the YLogs project at bit.ly/YLogs and you join our community Slack channel to talk to me, to some of our engineers, to people who've been thinking about this and working on this for a while, if you do both of these things, then you can submit a form with just the relevant info. We're not going to be asking you a whole bunch of questions, not going to ask for your name or anything like that. Just give us the GitHub username that you used to start the project, the email address that you used to join our Slack, and an address where we can send it, and we'll send you some swag. We're still figuring out what that swag is. Right now, we're thinking probably t-shirts, it might be mugs, but the point is that swag is in progress. And if you want to get yourself some swag, just follow these three easy steps: bit.ly/YLogs, bit.ly/YLogs Slack, and bit.ly/YLogs swag. So if you do these three things, I will personally mail you a t-shirt, a mug, or whatever other kind of swag we end up deciding to use. So thanks for coming, everybody. I really enjoyed getting to give this presentation. I'm looking forward to answering any kind of questions that you might have. You can either ask them in the live chat, or alternatively, you can send me an email. My email address is danny@whylabs.ai. You can message me on Twitter, where I'm @dlebs. Or if you want to get involved directly with an engineer instead of talking to an intermediary, you can also join our community Slack, as I mentioned earlier. And if you do so, you're going to get some swag. So thanks for coming. Feel free to ask any questions that you might have.